Alright guys, so, here we go. We're going to be doing a little work for our study guide on math. And kind of want to give you a little bit of a incentive for continuing to do these videos. So, when you get your math part, if you would write this statement right here, okay? You don't need to be telling anybody this. This is just for the people that are watching the videos. Write this statement next to your name, next to the math part. And if you write that, then I will give you something to kind of help you out here on the test. So here's your little reward for checking these out. Here we go. Let's get it going. Alright, so you got your trusty little calculator ready to rock, I assume. And we'll get it going. So the first one is pretty much T-catch. You throw it up in the air, miss it on the way down, and we can start to deal with this kind of problem. So, sorry, I'm all messed up here. Alright, here we go. Vertical motion with initial velocity problem. So, do what we always do and create your position time graph to begin with. So clear out everything you got in here and let's put it in. So negative 4.9 x squared. That doesn't change on Earth. We can always begin with that. Now hunt down the important things, like the initial speed and the initial distance. So we put in plus 12x. That's how fast we threw it. Plus the initial distance, 75. And this will take care of it for us, right? Here comes our parabola. You may want to, adjust your window to make it work. A good Y max might be something like 100. That should look, nice. I got my Y min all messed up, but, don't worry about it. It doesn't have to be perfect. So we need to find the maximum. We're going to go through and we're going to find everything we need about this particular parabola. I'm going to put a little post-it note here on the side, and this is all the stuff I'm going to need. So remember, we want to find the time it lands, the negative root, the maximum, and what time that occurs. We can pretty much figure out everything we need except for maybe the velocity it lands with when it hits the ground. This would be a good way to get us going. So we go calc, we go max, move to the left of the peak, move to the right of the peak, and then we want it to tell us how high it went. So we find the peak to be 82.3 meter, and the time was 1.22 seconds. Then we find the time it hit the ground with, so we want to zero that and move over here to the right. We go to the left of the zero and to the right of the zero, and we hit enter, and we get 5.32 seconds. So that's that. And then to the left, we do calc, and we go 0, and we're going to do the left root. So we move it on over, past the Y, on down, and we got the negative, and we go up here to the positive, and we press enter again, and you get negative 2.87. So these are our important numbers that we need. Now let's create the velocity time. So to do that, we plug it in at number 1. We find we get negative 9.8x, and then we have our initial distance, or our, let's see, v equals v naught plus at. So we have our initial velocity 12. And then we want to come up here and kind of turn this one off, right? Hit graph. Whoops. Nice, right? So I forgot to make it negative. Always negative 9.8. And we're going to graph it again. Now it looks a little bit better. You can see it going on down. My scale is really not the best scale. When I draw it over here on the post-it note, I'll try to represent it a little bit better. So this is our initial velocity. This would be 12, and we cross the 0 at 1.22. And what we want to know is how fast the v is when we cross 5.32 seconds. So the way we accomplish that is with a value. So our value being 5.32. And so we get a negative 40.14 meters per second. So now we're ready to answer everything. That's really the business here. With that, we can get everything we need. So I'll kind of go through now. I've got a little answer sheet from previous years, and it should help us kind of understand what's going on. So I'll have my post-it note right here too. That's going to be important. The first question was, how much later does it reach the bottom of the cliff? Well, one way to do it obviously is just take that positive root. So that's 532. You can also do it with number 3. Plug your numbers in, get 5.32 seconds. Now you can also do it by doing the two-step. So you could find the velocity hits the ground and plug it back in. I don't feel as that is all that useful though, so I'm just gonna stick with that. B, what is the speed just before hitting? So what is its speed just before hitting the ground? Remember, we found that by putting in the value. We got -40. Here on this example, I did it by plugging that time in here and getting it using number 1, or you can also do it with number 4 and solve it straight away without the time and get -40. Don't forget to make it negative as it's going down when it hits the ground. Okay, C wants to know, what does C want to know? C wants to know what total distance did it travel up and down. So up and down distance. I don't think we've really done this one before, but if you just think about it, it shouldn't be too bad. Using the calculator first, we started at a height of 75. So really what you have to do is you take 82.3 minus 75, and then you want to add 75 to that, right? So this would be up, that'd be that much, get to the apex, plus 82.3, my bad. And then you come back down to 82.3. So that's going to be 7.34 right here. And then you're going to add that to the distance, 82.34. And you get 89.68 using the calculator. That's probably the best way to do it. You can also find the max using number 4 and get 82.34, but the calculator really is the way you guys should be doing it, just for a time kind of constraint thing. D, you actually don't need to have any math for at all. It's just how fast you have to throw it from the ground in order for it to land with an equal magnitude of speed. And so, if it lands at -40.14, and we wanted to throw it from the ground, and we wanted to go equally as high as before. Remember, before we were kind of like up here at 75, throwing it up, right? So if we want to throw it from the ground, we just have to throw it with the same speed it would land with. So if it lands at -40.14, obviously we got to throw it up at 40.14 since that gravity's constant. So no math. It's just a quick little easy question to see if you are doing the study guide or not. So I would say C and D are things that people that don't do the study guide might miss if they don't really know their business. Okay, so let's do T-catch now. So this is one that you really got to be aware of because this is different. So how is it different? Now we have a D-naught. So who has a D-naught? Well, constant velocity. So a car traveling at constant rate of 31 past a police car. Speed limit is 20, so police car, that's bogus. Don't worry about 20. So police car goes after him, accelerates at a rate of 5 meters per second squared to catch the car. What times are the cars side by side? 2 answers at the beginning and sometime later. So remember, the problem starts. The problem begins when they have the same position the first time. So that's time 0. So how do we get this in our calculator? Well, we'll do a little post-it note action again. Okay. So you set 3 equal to 3, and if we only put the important parts in, we're going to have D-naught. Now listen, this is very important. Because he weights, the accelerator weights, it has a D-naught. So we have D-naught plus V-naught T. That's going to be equal to 1/2 AT squared. This would be constant V, and this would be constant A. Constant V, constant A. And we just put our numbers in. Now, if he waits 1 second, right, it says it right here, we're going to have a d naught. So if you go a constant velocity of 31 for 1 second, you're going to start at 31 meters in front of him. And then your v naught is still 31 as well. So we get this. That's what we're going to throw in our calculator. You know, constant acceleration, that's going to be half of his acceleration. So 5, half of that would be 2.5. And then we have x squared. That'll represent the parabola. So we go in here until our y equals, I still got this from the last time, we don't need that anymore, so goodbye, see you later. And we want to put in our stuff. You know, on the test, you're going to wait something besides a second. What happens if you waited 3 seconds? Well, that would be 93. 2 seconds, 60, 62, okay? Understand this varies by how long you wait, but the constant v part doesn't change. 31x plus 31, right? We'll put that in as one line. 2.5x squared is what we want to put in the next line. And then we want to get our graph. So I hit graph, constant velocity. See how he's starting in front of him right there? He's got a head start. My window's jacked up again, so I'm going to make my x max maybe 30 and my y max maybe 300 and see what that looks like. Now he's got that head start, and here he comes trying to catch him. We're going to have to make our y even bigger. So we'll go into window again. We'll make our y max. Let's try 500 this time. We'll see what that looks like. And he's coming up, and boom, that's where he catches it. So we're going to have 2 times. We'll have a time here, and we're going to have a time here. Remember, the problem began when he went after him. So, you know, if he waits time, there's going to be time that's occurring. This is t-catch, so we're just going to try to find the catching time. So I'm going to go to intersect number 5, and I'm going to work up to that intersection and find out what it is. It's 444 for a distance and 13.3 for a time. So t equals 13.3 seconds. So let's answer the question. So what time is the car side by side? 13.3 and 0. Also, what distance does this occur? Well, it's not really 0, right? It'd be negative time, which you can't have. Also, what distance does this occur? This distance is right here on the intersection, 444. So it occurs at 444 meters. So D and T. Easiest way to do it, intersect it. Strongly recommend it. In fact, if we go through and then we find this negative root, surprisingly, you will find it occurring at -1. So that's, you know, -1 seconds and 13.3 seconds. Those are the 2 times when they have their same velocity. And the parabola doesn't really totally match because this is kind of a hard thing to explain, but the parabola has kind of a flat portion to it. So if you take 13.3 is what's really mattering. Let's not worry so much about the -1. But that's the truth of it. And I don't want to get into that a whole lot. That's kind of a difficult thing, but it does affect t-catcher when they have the same position. Alright, so now we work into our integral problem. So because we're already like 13 minutes in here, I'm going to try to speed things up a bit. So we make our VDT chart, find a good thing to use, and that would be kilometers per hour, kilometers and hours. Go through, fill it in, 3 and 1.5 and 0.5. Then we're not moving. Then we're moving forward again with a velocity of 2 for an hour, and gives you 2, you know, represented here in my graph with positive values. Here's where I'm not moving, and I have a -3.5 velocity for an hour. And then when you're all done, you make it back as you have 3.5 and 3.5, and you can see it represented here in my graph. I feel that this one's a pretty easy one. I think the one on the test will be harder than this. I think it has 5 different situations. So be aware of that they're not always going to be this easy. But the idea is that we find the area of the shapes and we plot the area's position, and that's why it's called an integral. New graph based on area is an integral. Okay, now the one you all been waiting for. This one right here. I'm not going to really worry about numbers too much. I'm just going to worry about areas. So that we'll say this has a positive area, this has a positive area, this triangle has a positive area, this triangle has a positive area, this has a negative area. So for the first 4 shapes, we're going to be going forward. Notice that this has a slope of 0, this has a negative slope, this has a positive slope, this has a negative slope, and this has a negative slope. So all these refer to the slopes. And the slopes will kind of tell you about the acceleration. So I think I'll start with the acceleration time graph. So I'm just going to quickly sketch a little, x, y thing here. And we're going to put meters per second squared here. And then I'm going to go through and just try to show you how we plot this. So if I find the area of that object, it would be positive. Don't worry about numbers right now. And then the area of this isn't as big as that. It's about half, so I'm going to continue to go up in about the same time period. Notice I'm trying to use these as my time scales. I'm just trying to line them up. Maybe if I bring it up a little bit more, you can see how I'm doing that. And then I start to, same shape again, so the same distance here again. And then even one more triangle. So I'm still going forward. And then finally I have a negative area in the very last shape. And it's about the same as that one. So it's going to put me pretty much right about there. So I'm just plotting my area. Turns out I lied. I'm doing my position graph. I'm sorry. So here's our areas, right, inside the objects. So what happens at the beginning? Well, if it's a square, you're going to connect your dots with a straight line. Okay, and then that straight line is going to move up into a curve. So that's a parabola. Whatever slope you leave off is the slope it should go. And then see how the hypotenuse of the triangle is negative, and so the parabola curves to approach a slope of 0. Then it's going to curve up as we continue. Now we have a positive hypotenuse, then another negative hypotenuse, and then we have another negative hypotenuse, and it's going to detract from the area. So you get something like this. This is the only portion of this entire graph that is linear. These are all quadratic. And this would be the final point. Now, like I said, I'm not even going to worry about numbers. Now, you can do with numbers if you want. You can actually find, what the slopes are. You can actually find the exact areas, and that might help you. But, like I said, I'm not going to be too much of a stickler. I only put that on there if you want it to help you. Okay, so then now, like I lied before, right? So now we're going to do the acceleration. So for the acceleration time graph, we're going to plot the slopes. So you line it up and you look at your slopes. Here I had 0 slope. So for the first thing, I have no acceleration. Remember, constant velocity, cruise control, no acceleration. Then I have a negative slope. You can look at the hypotenuses. It curves for about that long. Then I had a positive slope. So I come up here, positive slope, then back to negative slope, and then that negative slope just continued on. So when I'm all done, I can kind of look at all my graphs that I made. You don't have to box these up. You can if you want. But that's what's going on. So this is kind of a tough problem, but notice I didn't make you do any math in it. So if you can visualize what the graph looks like and not do any math, that could be something that could be done pretty quick. And if you look at the total time spent on the video, this was only a couple minutes, but you really got to know your business to be able to do it. So remember, everything I circled, I use slope to make this graph, and then I use area to make this graph. And if you want to actually calculate the area of a triangle, half the base times the height. If you want to calculate the area of the actual squares, length times width. Same thing here. If you want to find slope, very simple. You just use y2 minus y1, x2 minus x1, and that'll give you your slopes. So that's how you solve that one. And don't forget, right? If you want your little extra something on the math part, if you just write this phrase somewhere, something will be given to you. If you stuck it out this long, put a little underline on it, and then I'll know you made it all the way through. All right. Good luck to you. Questions, see me. I'll be around before, after school, and we'll talk later.